Hello, welcome to another one of my videos. This time we'll be talking about several different topics, first of which will be sudden expansion. So here we have a sealed cylindrical vessel filled to some height HI with fluid. And it's got an initial pressure above the fluid of 101,325 pascals, and the total height of the vessel will be H. And it has a cross-sectional area of AC. So now, at some point, when he pokes a hole in the bottom and fluid begins to stream out at some velocity. And as this happens, the water level will begin to drop. So what we want to do is find a function of the height of the water as a function of t. So in order to do that, first thing we need to do is to find the moles of gas above this water. So because it's sealed, the moles of gas in here will not change, but the pressure will. So because we know the initial conditions, we can solve for the moles of gas. So we have N equals PV over RT, and we want to solve for the initial conditions, so we're going to use P naught and V naught. And so V naught is going to be the area above the fluid, so it's going to be H minus HI times the cross-sectional area. That'll give us the volume. So N is equal to 101,325 is the initial pressure, times AC, H minus HI, all over RT. And so because this doesn't change, we're going to plug it back into the ideal gas equation again, but this time at pressure P1, when the height is not the initial height, once it has dropped some level. So that's going to give us P1 V1 is equal to N RT. So P1 is equal to N RT over V1. And V1 here is going to be the same cross-sectional area, but this time from H to large H. So P1 is going to be equal to, we'll plug it in, 101,325 AC times H minus HI times RT over V1, which is going to be AC times H minus H. And we still have the RT on the bottom. So now this RT will both cancel. We'll have an AC cancel. So now we have the pressure is going to be equal to 101,325 times H minus H1, or HI, all divided by AH minus H. And so this is a function for the pressure at any given height of the fluid. The pressure above the fluid for any given height of the fluid. So now that we've modeled the pressure at a given height, we need to use Bernoulli's equation to find the velocity as it exits from the vessel at point 2. So Bernoulli's equation, P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1 equals 0. And so we know that V1 is going to be approximately 0 because this cross-sectional area down here is so small, that velocity as it exits is going to be very high. And because this cross-sectional area of the fluid level is so high, that means the velocity is going to be very low to compensate for the volumetric flow rate. So this means comparatively to V2, V1 is going to be very small, especially when you square it. So this leaves us with P2 minus P1 over rho plus V2 squared over 2 plus G. So Z2 is going to be the bottom of our vessel, so we're going to say that's the elevation at Z2 is going to be 0, and Z1 is going to be H. So that gives us Z2 minus Z1 is 0 minus H, so that's negative H. I'm going to change that positive to a negative. And now we want to plug in P2 and P1. So P1 we've already written this equation for. And P2 we can think of a little bit more conceptually. So because this cross-sectional area is so small, it's going to go through a sudden expansion as it enters the open system. So because of this, there will be no pressure recovery. So the pressure at 2 will be equal to the outside pressure, which will be atmospheric pressure. So P2 is going to be equal to 101,325 pascals. So first we need to separate V2. So we have V2 over 2 squared equals GH. I'm going to keep this positive and flip around P1 and P2. P1 minus P2 over rho. So now we want to plug in P1 and P2. So that gives us V2 squared over 2 equals GH plus 101,325 times H minus HI over H minus H minus 101,325 all over rho. So as you can see here, both of these contain 101,325, so we can factor that out. And that gives us V2 squared over 2 is equal to GH plus 101,325. I'm also going to factor out this rho because it's divided amongst the entire thing, times rho. And then I'll have H minus HI over H minus H minus 1. And that's where that 101,325 came out. So now we need to finish solving for V2. So we get V2 is equal to 2 times GH plus 101,325 divided by rho times H minus HI over H minus small h minus 1. And this whole thing here is the 1/2 power, so we'll take the square root of it. So this is our function for the velocity at 2 based on the height of the fluid at any given time. So now that we have the velocity at point 2 as it exits the vessel, we need to figure out how it relates to time. So we'll have Q out. The volumetric flow rate at which it leaves the vessel is going to be equal to V2 times A2. But we also need to know how this Q out relates to the fluid level. So it's actually going to be the change in volume over the change in time. So as the volume changes with time, that will be equal to the water that exits the vessel. So all the water's in here, and so when some exits with time, it will show up with negative Q out. So now we can set these equal to each other. So we have d volume over dt is going to be equal to negative V2 A2. And we can change this d volume to be the cross-sectional area times the differential height over dt is equal to negative V2 A2. So that gives us the differential height dH dt is equal to negative A2 over A1 V2. And so plugging in V2, we get dH over dt is equal to negative A2 over A1 times the square root of 2GH plus 101,325 over rho times H minus HI all over H minus little h minus 1. And this will be the differential equation that we solve for when we code. So as you can see, we finally related it to differential time, and we have area at 2 and the area at 1, which are both constant. We have g, which is a constant, rho, which is a constant. So the only things that are not constant are the h, and that h is what we're going to solve for. So now on to the coding part. So now that we found our differential equation as it relates to the height of the fluid to any time t, we need to go into Colaboratory and solve this numerically using coding. So the first thing that we need to do is import NumPy, numerical Python, as MP. So this will just let us use all kinds of different mathematical functions like square root, which will be necessary when it comes to our V2 equation. And we also want to, from Skype.integrate, import solve_IVP. So because we're solving a question numerically, we're going to have a set of initial values, and we need to integrate upon these initial values to get our answer. So that's why we need to integrate this function. But we don't just want to find the answer, we also want to plot the answer. So from plotly.subplots import make_subplots. And so now that's just imported all the different libraries that we need into this code. So next is we need to define our differential equation. So we're just going to call this right-hand side. And as you know, differential equation always need to take an independent variable first, which is t, and a vector of the dependent variables, which we'll call y. So these set of these dependent variables, we actually only have one in this question, which will be the height. So h is going to be equal to the first part of vector y, since we only have the one dependent variable. So now what we need to do, we need to define our v2 equation. So v2 is going to be equal to np.square root. This will return the square root of it, and is why we imported numpy. So 2 times g times h plus, we'll call p2 p external now, and divide that by rho. And we're going to multiply this by h minus hi divided by h minus small h minus 1. And as you can see, this is the v2 that we derived on the board previously. But we don't just want this v2, we want to return negative a1 divided by, or we'll call this the area of the whole, divided by a c, the cross-sectional area of the entire vessel, times v2. Go ahead and shift enter, and as you can see, that works. But we actually have a whole lot of variables in here that we have not yet defined, so we're going to go ahead and do that now. Starting with g, which is going to be 9.81, and then I'm going to add a comment so I can get my my units in there. And then the next step, we'll have p external, which is going to be equal to 101.325 pascals. Next is the initial height of the vessel, or the total height of the vessel rather, which is going to be equal to 1 meter. We have the initial height of the fluid, which is going to be 0.9 meters. We have the area of the hole, which is going to be equal to 1 times 10 to the negative third meters squared. We have the cross-sectional area of the vessel, which is going to be equal to 1 meter cubed. And we're also going to have our density. So rho is going to be equal to 1 times 10 to the third kilograms per meter cubed. So now we've defined all those. We can go ahead and just see if this returns a value. You can see it does actually work. So our differential equation will run. So next up, we need to figure out the event at which V2 is equal to 0. So because what we want to know is how high the height of the fluid is when the velocity exiting reaches 0, we need to be able to find out when, at what time t, that V2 is going to be equal to 0. So we need to define some equation for that event. So we'll just call this V2 0 event. And it's also going to take in the dependent or independent variable t and vector y. And again, h is going to be equal to y0 for the same reason as before. And then we want to return just the v2 this time, because we want to see when this v2 is equal to 0. So 2 times g times h plus P external divided by rho times h minus hi divided by h minus h minus 1. So that'll give us what we want for our event. We also want this to terminate at this time. So we're going to say v20 underscore event dot terminal equals true. Oh, I spelled that wrong. That's why it's given it an error there. So nice. We can see that that worked. So now what we need to do is we need to solve our IVP, our initial value problem, and see what the actual results of it are. So in order to do that, we'll just say, we'll call that results, REZ, or RES, equals solve underscore IVP, because we want to use that function. And we want to solve for right-hand side from some time interval. So I need to have an end time here. So I'm just going to make that, let's say, 10 seconds. So from 0 to t end. And our initial height, our initial dependent variable, is going to be hi. And we're going to be using the Radeau method. Make sure I spell that right. Dense output, if I can spell, is going to be equal to false, or true rather. And for events, we want to use the event that we just found, which is v20 underscore event. And that'll be our RES function. The t end is not to, oh, it's because I haven't updated this. And now it should work. SP, where did I put SP? Let me figure out what I did wrong real quick and then I'll be right back. So I was able to figure out my mistake pretty quickly. So right here, instead of np.square root, I had sp.square root, so that just wasn't doing anything for me. So now I've changed that, everything should work. So great, now I just want to return this res function and see if it did what I want it to. So it says termination event has occurred, which is good. It means that the solver stopped at the event that we specified. And we can see that this event is 4.56, etc. So this is going to be the time at which v2 is equal to 0. And now that we have this, it's time to plot. So the first thing we need to do is specify what our time plot will be. So these will be our x values to correspond with the heights. So we'll just call this t-plot is equal to np.linspace. I'm going to use this because I want evenly spaced intervals of numbers, and this will give me that. So I'll start at t equals 0, and I'll go until that event that we just specified. And as you can see, I'm doing a double array grab here, and this is because, as you can see, the T event is an array within an array. So I need to use a double there in order to get that value 4.56. And then let's just go ahead and get 500 time values. That should be plenty. So now that we've done that, we need to make our figure. So in order to do that, we need the make subplots that we imported earlier. And then we need to add something to this subplot, so we'll add scatter. So this will let us input our x values and our y values. So our x values, as I said, are going to be the t plot values, and our y values are going to be equal to heights, which is stored in this res solve function. So y is going to be equal to res.solve, and it's going to solve it at all of the times in this t plot array. And now we want to update the layout just to make sure the graph is big enough. So to do this, I'm just going to say the width is going to be equal to 700, and the height will also be equal to 700. And then for the template, I'm just going to say Plotly dark, because that's the one I like the best. I think it looks nice. So we're going to shift enter there, and hopefully that'll return a plot. So great. So this returns our plot of time along the x-axis versus the height of the fluid along the y-axis, and it stops when the water stops exiting the barrel because of the pressure buildup. So this is what we wanted to solve for, and this will be our final graph for that initial value problem.